Okay, guys, welcome back to our final discussion about aspects of steady state enzyme kinetics and how they're useful for understanding really important basic things in biochemistry. Now, over the last couple of lectures, we've been spending a lot of time talking about um, what steady state enzyme kinetics means, how you get to this idea of an initial rate, the way in which in excess substrate enzymes behave, this idea of saturation kinetics, and these important kinetic parameters like Kcat, Km, Kcat over Km. And I pointed out at the end of the last lecture that as useful as steady state enzyme kinetics is for getting information like that, in terms of understanding the real details of enzymatic mechanism, it's sort of a limited utility. It's sort of your first step, but it only gets you so far in really understanding how enzymes work. But one of the places where in steady state enzyme kinetics is front and center and is extremely important is in understanding how enzyme inhibitors work, right? And if you think back to that example that I started with when we began really start talking about enzymes, this idea of enzyme function being something one would target when making a drug, for example, that HIV protease, understanding how good a given inhibitor is and how it works with respect to enzyme catalysis is incredibly important. And this is where steady state enzyme kinetics is incredibly useful, right? And is used as a frontline tool, right? In a really big way, right? So before we start talking about this in detail, we need to make a distinction, right? What I need to distinguish between or point out the difference between is two different the largest possible class of enzyme inhibitors. So those are so-called reversible versus irreversible inhibitors, right? Now, most of what we're going to end up talking about is going to fall, or essentially everything is going to fall on this reversible side. But to distinguish that from this other type of inhibition, so-called irreversible, we need to think about what that means. And so an irreversible inhibitor is one that essentially binds so tightly to the enzyme, it never comes back off again. And usually that's going to mean a covalent modification of the enzyme. I'm sure there are exceptions, but usually that means some sort of an inhibitor that covalently alters the structure of the enzyme, usually the active side of the enzyme, in such a way that it can either no longer bind substrate, or even if it can't do chemistry anymore. And a classic example of that, of course, is the inhibition of serine proteases by molecules like phenyl methyl sulfonyl fluoride, molecule that looks like this. You guys, anybody who's ever worked in a protein chemistry lab has come into contact with this particular molecule because it's such an incredibly useful molecule in terms of killing many serine proteases. All right, so that's the molecule. It happily snuggles down into the active site pocket of many serine proteases. And if you then, and positions that sulfonyl group very close to, almost just in sort of perfect orientation with respect to the active site serine residue, right? So off over here, say trypsin, rest of the enzyme here. And of course, we have our histidine over here and hydrogen bonding distance, that serine hydroxyl. And in the same way that trypsin would normally do its thing, attacking that serine nucleophile would attack the carbonyl oxygen, it will happily attack that sulfonyl group, liberating fluorine, resulting in this hydroxyl or this oxygen sulfonyl conjugate that is basically not reversible. Technically it is. It will hydrolyze back, but the hydrolysis is so slow. This effectively kills the enzyme. Right. Once this happens, you get that sulfonyl adduct on the active site serine residue, the enzyme's dead, right? Okay. Now, there are lots and lots of examples of this, many enzymes. There are well-known covalent modifiers that will kill them. But an important point here is that in general, irreversible enzyme inhibitors are terrible drugs, right? And the reason they're terrible drugs is because they're incredibly toxic, right? And usually the name of the game in developing a therapeutic, a drug molecule of some kind, when you're targeting an enzyme, is you want to modulate the activity. You don't want to wipe the enzyme completely out, right? So irreversible inhibitors, by and large, are not things you're going to find used as effective therapeutics when you're talking about inhibiting enzymes in a medical sense, right? So, excuse me. All right, so just important to be aware of the existence of these irreversible inhibitors. But what we're going to really be talking about again is this class of molecules, the so-called reversible inhibitors. All right. This is where we're going to be focused. And what that means is we have to think about molecules that are going to be binding essentially dynamically or reversibly to the enzyme or to enzymes that we want to try to alter their activity, inhibit their activity, right? Which means we have to think about layering on a binding phenomenon, small molecule binding phenomenon, on top of the steady state kinetic behavior we were just talking about. We have to put those two ideas together, right? And there are three sort of essentially large classes of ways in which this can be described. We're going to go through each one of them and think about how these different types of reversible inhibitors modulate steady state enzyme kinetics.